Our next speaker is Ilya Shkredov from Stiklov Mathematical Institute, and his topic is growth in Chevalley groups and Zaremba's conjecture. So please, Ilya, start.
Thank you for the invitation. I would like to think about Chevalley groups and about applications of such groups to number theoretical problems and additive combinatorial problems. I would like to say informally what is a Chevalley group is, because it requires a lot of time to give the precise definition. So let me just quickly describe what the place of the Chevalley groups in mathematics. There is a famous classification of finite simple groups theorem, which say that if G is the finite simple group, then G belongs to one of three infinite series or 27 finite sporadic groups. Infinite series are Z over Pz. P is a prime number. Alternative group for n is greater than 5, and so-called groups of Lie type. For us, groups of Lie type are more or less Chevalley groups. It's more or less the object of our talk. Of course, formally, not every Chevalley group is simple group, or group of Lie type is Chevalley group, but nevertheless, it's not really important. Okay, so it's, as I said before, it's difficult to describe what Chevalley group is, but you can just use this classification of Chevalley groups. And Chevalley groups are divided onto several parts. There are classical groups like SLN or special linear group, also unitary group, symplectic group, and two orthogonal groups. These are so-called classical or matrix groups, which have matrix representations. Another Chevalley groups are, they have no matrix representations, and these are if 6, 7, 8, F4, and G2. Nevertheless, what does it mean? Also, there are a few series of another Chevalley groups, Steiner group, and Suzuki-Rie groups. So let me give you the simplest example of Chevalley group. SLN of f of q, it's our actually main object, the simplest example of Chevalley group. We have here maybe the most important subgroup, so-called Borel subgroup. It's the standard subgroup of the upper triangle matrices. In SL2, in SLN, we have the restriction that the product of all elements equals 1 modular Q in the field Q, and so it's the standard Borel subgroup, but if you conjugate such thing, it's also Borel subgroup. So if it's the Borel subgroup and a Borel subgroup, it's any conjugation of this one. Okay, another, so I would say that the word of subgroups in Chevalley groups is infinite. It's infinitely difficult, but there is a very understandable series, and maybe the only series of subgroups in such groups. These subgroups are called parabolic subgroups. By definition, it's all subgroups which contain a Borel subgroup. In our case, SLN, it can be described easily. So you have a blocks of square blocks and any elements upper to these blocks. One can show that it's very simple, that there are 2 to the n-1 of parabolic subgroups. For example, in SL2, we have just SL2 and the subgroup of the upper triangle matrices. And this number n-1 is called rank of Chevalley group. I don't want to define it precisely either. Okay, so what's interesting about Chevalley groups and about simple groups and how we will use it. There is a huge and very interesting Babel conjecture which asserts that if I have any subset of any finite simple group which generates a group, so I write it in this way. So A generates G by taking products or inverses of A, it's not important. Then actually this A generates my group G very effectively. It means that there is N which is rather small, just basically log to the sum power of the size of G, such that A to the N equals G. So if I have in principle generation, then I have it in very effective way. It's a very interesting conjecture and exciting. And it was Harald Helfgott who proved the first result in this direction, first serious result in this direction. He proved Babai's conjecture in SL2, and after that, another mathematicians like Brouillard, Green, Theo, Piper, and Szabo generalized his method, and more or less they proved that Babai's conjecture holds for any simple group, finite simple group of Lie type. So they proved that for any such group and any set which generates G, either the cube of A, so it's A times A times A equals the whole group, or I have this exponential growth of A. In particular, it's an easy implication that for such N, I have A to the N equal G. The only bad thing concerning this result that this power C depends on the rank, but for finite rank as in SL2, it's not important. So in SL2, conjecture of Babai takes place. So the aim of my talk is another problem more easily. It can be formulated more easily. So I don't want to generate the whole group. I want to intersect I want to find an intersection of A to the N with a fixed subgroup of my Chevalley group. For example, I can take parabolic subgroup. So is it true that if A generates the whole group, then it intersects a fixed parabolic subgroup? There is a result in this direction. It was proved by Lanzuri and Zeitz that for any Chevalley group, there is the following low bound for the minimal dimension of any non-trivial unitary representation of the following form. Q is size of field, R is rank, and this bound is perfect because Q to the R is more or less G over P, where P is the maximum parabolic subgroup. So this bound cannot be improved. And it means that Chevalley groups are quite random in the set of Gauss. It means that actually for very large set, it doesn't matter generating set or not, I have some growth. This concept of quasi-random group was coined before Gauss by Sarnak and Xue, and before them by Hensley. So the corollary of the result is the following: I take any large A, which beats a little bit this bound, right? So A is larger than the maximum parabolic subgroup, and then A to the n equals G for very effective n. It's a corollary of this lower bound for dimension. It's a corollary for these quasi-random properties of my Chevalley group G. I improved the result in my settings, so I take a parabolic subgroup P, and I want to find n such that A to the n intersects P. And if I decrease this R by 1, then I can guarantee that A to the n intersects P. This saving by 1 is crucial for us. You will see in a minute that this one corresponds to Hausdorff dimension 1/2, which Hausdorff dimension, and this Hausdorff dimension corresponds to Hensley's conjecture. Okay, another result about growth relative to parabolic subgroups is the following. I take any set A, and I want to say something about the product of A times parabolic subgroup P. Of course, if I have A of this form, X times P is just the union of cassettes of P, then A times P is A, so it doesn't grow at all. On the other hand, if I have a left hand cassette, then P times A equals A. So my result is the following, that for any A, either A to the P or P to the A must grow. So this maximum is greater than this quantity. For example, if A is less than P, then maximum is greater than size of A times square root of Q. And this growth is also important for us. Also, I have some mild restrictions here. I've written it like P, A doesn't intersect P, but it's not important. It can be avoided, more or less. Okay, so it was a result about growth relatively to multiplication by parabolic subgroup, and it was a result about intersection. And now let's find an application of this growth result to continuous fraction and to SL2 of FP. So it turns out that this theme is connected with well-known Zaremba's conjecture from the theory of continuous fractions. So I have a real alpha, and I have the decomposition of alpha onto continuous fractions of the following form. Yes, 1 over C1 and so on. And Zaremba's conjecture says that for any prime P or any number, not just prime, I can find A such that if I consider the finite continuous fraction expansion, C1 and CS, then I can find A such that this ratio has all partial quotients C1, CS are bounded by 2, are bounded by 5, sorry. We will be later a little bit. Okay, so it's a strange looking conjecture. it's not to be true for log of p instead of m. So m when m tends to infinity. It's known for composite Q and so on and so forth. There are a lot of mathematicians who have made a coin in this area. For example, let me mention a beautiful theorem of Bugan-Kondarovich, who say that actually Zaremba's conjecture holds to be true with any m and with these zero terms. So for almost every q from 1 to m, all but this number of q satisfy the Zaremba conjecture. And they took m equals 50 in their result. After that, their results were improved by Frannikov, Kahn, and other mathematicians, and the best result here belongs to Kahn, who proved that for m equals 4, even for m equals 4, almost all q satisfies Zaremba's conjecture. So let me say a little bit about the intuition which stays under the Zaremba conjecture. It was a beautiful result of Hensley, who calculated the following Hausdorff dimension of the set of real numbers. So consider now a real number alpha with all partial quotient bounded by m, and then Hausdorff dimension of this set, of this counter type set, can be calculated as follows. For example, W2 is the following. Number is greater than 1/2. It's important for us. And I would say that this estimate was known by Hinchen at the beginning of 30s. Okay, so actually Hensley conjectured much more strong thing. So now instead of this sets with partial quotient bounded by m, take an arbitrary alphabet. So instead of alphabet from 1 to n, take any finite alphabet. Then Hensley conjectured that if the Hausdorff dimension of this correspondent counter set is greater than 1/2, then an analog of Zaremba's conjecture takes place. It means that for any relatively large p, I can find a such that all partial quotients belong to a. Okay, so what was the intuition of Hensley's hypothesis? He considered the following finite set, so it's not infinite continuous fraction, but finite one. And he considered the following fractions such that O as j bounded by m and u and v from 1 to q. Then he calculated, it's rather easy, that the size of this set is just q to the 2 wm. Wm is the dimension, Hausdorff dimension from this slide here. Okay, so if you're interested in one parametric set, so now we fix our denominator u, v, pardon, then if we believe in the uniform distribution over the denominators, then we must divide this bound onto the number of denominators. And I obtain what? 2 to the p to the 2 to the wm minus 1. And if Hausdorff dimension is greater than 1/2, then this quantity is positive. And hence, Zaremba's conjecture has a chance to be true. So once again, in a strong form, Zaremba conjecture say that size of this set equals this quantity, and P proved last year with Moshevityn and Murphy that actually the same upper bound for Zm of P takes place. And moreover, we proved that if you exclude epsilon s interval from the middle of your continuous fraction expansion of A over P, then you can prove Zaremba's conjecture accepting this small interval of length epsilon. So I think I will skip pure combinatorial consequences of this, and let's say a little bit about our new results. The first one is in our common paper with Moshevityn. It's so-called modular Zaremba conjecture. Now we take a prime P, and we want to find Q maybe larger than P. You see, for us is P to the third. Such that Q is divided by P, and A over P has all partial quotients bounded by M. Firstly, this result was proved by Hensley with very huge constant, which is now 30. And he used a completely different method, our method based on growth in SL2. And moreover, we proved modular Zaremba conjecture in the following form. If you allow to increase your 30, this constant 30 to large constant C, then you can even find A over Q such that all partial quotient bounded by 2, like in original Hensley's conjecture. And my result is the following, that actually it's possible to find Q such that Q is P to the 1 plus epsilon for any epsilon, such that all partial quotients of A over Q is bounded by M. Literally, if you take epsilon equals 0, this is equivalent to Zaremba's conjecture. Okay, so moreover, this method allows to obtain modular Hensley hypothesis. If you have a finite alpha bit alpha and the Hausdorff dimension of the corresponding counter set is greater than 1/2 plus delta, delta is positive, then you can find Q, which is comparable with P. It's just a power of P, such that Q is divided by P divides Q, and such that A over P Q has partial quotient bounded partial quotients which belong to A. So modular form, this modular form of Hensley conjecture takes place. Okay, so I have a few minutes. I want to say some words about the idea of the proof. So and how SL2 helps here. So having a rational number QS over PS over QS and the previous approximation of this number PS minus 1 over QS minus 1, you can calculate the following matrix from SL2 of FP. So you just multiply such matrices, and this 2x2 matrix is just corresponds to this rational numbers. It's not from SL2, but if you take even S, it will be from SL2. And moreover, consider not all such matrices, but with our conditions, Cj are bounded by M, and this QS is less than P. So it just fair product, not in FP even, but in Z. Then by Hensley's lemma, the size of A is just the following quantity. It's P to the Q, P to the squared, and to compare, the size of SL2 is P to the cubed. So it's a large subset of SL2, but not the whole group. Okay. So the next step is the following. Consider after that the powers of A. Powers are taken in SL2 of P. And suppose that you can find a zero element in A to the N, say Q to the S. Then you see that my quotient PS over QS has the denominator which is divided by P. And because of this QS belongs to power, the power of A, it's easy to calculate the size of QS. It just basically P to the N, 2P to the N. So I want to find a zero in my power A to the N. And it's not important to have QS to be zero. You can take any element to be zero. It's an easy theory of continuous fraction. So for me, it's more convenient to find QS minus 1 to be zero. So basically, I want to find intersection of a power of A with our standard Borel subgroup. So now our question is the following. Can we find A such that A to the N intersect B? It's a purely additive combinatorial problem. So the first trick is that this equation can be rewritten in this way. I can multiply B from left to the right, and these two sets have appeared. And we know by our first result that the maximum of these two guys is large. Then it means that I have one of these sets to be P to the 5 over 2, that it's much larger than the size of my original set A. So I have the growth. And if you say something not true about this set A to the N using the half-got result on growth in SL2, then you will obtain modular Zaremba's conjecture. So what about modular Hensley conjecture? So now our dimension is greater than 1/2 plus delta, and it means that the size of A is greater than 1 plus delta. In SL2 or PSL2, there is a nice and very classical classification of its subgroups. They are just Borel subgroups and their conjugations. The size of Borel subgroup is P to P squared. And there are general subgroups of size P, basically. And also there are possible finite groups. And you see, if our set is so large, then we do not care about variance 2 and 3. We want just to find an intersection with a conjugation of Borel subgroup. But here we have a result that if A is relatively large, then A to the N must intersect any parabolic subgroup, and in SL2, any parabolic subgroup is just a Borel subgroup. So P equals B, R equals 1, and applying this theorem, you find a non-trivial intersection. So, and it gives you this result in the direction of Hensley's conjecture, model conjecture. Using I don't want to talk more about it. So using some more careful analysis concerning the representations of my set A, you can obtain this result with 1 plus epsilon. Basically, what can you say about representation? Basically, you can estimate the energy, the multiplicative energy, non-commutative energy of A, and you can estimate it not trivially. It gives us that my set A, which grows from continuous fractions, this set must be uniformly distributed in SL2. And if my set is uniformly distributed, then I can solve this equation with 3 variables. It's more or less standard thing. And also you can say something more about A, B, and BA for some specific subset of A, but it's another story. Thank you for your attention.
Thank you, Ilya. So it seems that there is no question. So thank you again.